Augmented reality refers to the introduction of virtual content into the real world. Here, the cartoon frog is superimposed onto the card so it appears to be a real part of the scene. Typically, the user wears a head-mounted display with a camera attached to the front. The images from the camera pass to a computer which introduces the virtual content and displays the image to the user in real time. In order to make the object appear to be a real part of the scene, the correct view must be determined in each frame. We associate the object with a two-dimensional cardboard marker. For each frame, the image is thresholded, connected regions are identified, and their contours are found. If the region matches the marker template, we accurately measure the position of the corners. These corners uniquely identify the position of the marker in the scene, allowing us to introduce the virtual content. In this project, we extend this technique by introducing 3D live captured content into the world. In previous work, two-dimensional video streams were superimposed upon markers to create a portable augmented reality video conference system. This project extends these techniques into 3 dimensions, as seen here. Given that we know the position of the marker in the scene, the main technical problem is to generate the appropriate view of the subject or actor for each frame. In order to do this, we build a 3-dimensional model of the actor using a shape and silhouette algorithm. The input to the system consists of 15 simultaneous video streams. 14 cameras are placed around the subject and 1 above his or her head. In order to generate an arbitrary viewpoint, we construct an image-centered model. The broad principles of the algorithm are as follows. Consider the problem of generating a novel view of this 3D teapot based on measurements from several cameras. The first step is to classify each pixel in each image as part of either the teapot or the background. We project light rays through the pixels which are classified as belonging to the teapot. This defines a minimal region of space in which we know the object must be located. We repeat this process with a second camera. Hence, the object must be contained within the intersection of these regions. Each subsequent camera carves away at this volume until what remains is a representation of the shape. We can then define a virtual camera at a new position. We project light rays through each pixel of the virtual camera and find where they intersect with the teapot. The color of the virtual pixel is estimated by considering the position of this intersection in nearby real camera images. The algorithm can generate novel views of this kind at 30 frames per second with less than 100 milliseconds of delay. Furthermore, it is extremely robust and requires no special hardware. We can generate novel views from any angle. As you can see here, we can capture more than one actor at one time. As this sequence shows, we can also buffer the video to disk and introduce special effects such as freeze frame. The principal interest of our lab is in enhancing remote collaboration. Current video conferencing technologies cannot fully express non-verbal cues, and remote communication suffers as a result. Hence, our main application is in video conferencing.
Hi, I'm here for the audition.
Okay, and what's your name?
My name is Joe West.
Okay, Joe, could you tell me something about your previous acting experience?
Yes.
Our system realistically introduces the actor into the world, together with appropriate 3D sound, which solves many of these problems.
I was the part of the donkey. It was a great role.
We can also use the system to generate live 3D avatars for interactions in virtual spaces. We present the example of a guide to a virtual art gallery. Notice how the actor here can gesture to objects in the scene, interaction that is extremely natural. Since we have generated a 3D model of the actor, realistic occlusion is also easy to implement. You could imagine an architect walking his customers through his building and discussing the details with them. We also consider augmented reality interaction with a collaborator in a virtual environment. We can use the tangible card marker to pick the collaborator up and move him aside. We can change the virtual environment by turning over pages in a book, and then we can replace him. We have developed these tangible interaction techniques into a game. We use a marker to try to drop objects onto the collaborator's head. The person in the virtual environment attempts to jump out of the way in real time. It should be noted that there remain a number of unresolved practical problems. The system requires a lot of space, and several computers are needed to process all of the video streams in real time. It is not possible to maintain eye contact for two-way video conferencing if both parties are wearing head-mounted displays. And there are a number of other disadvantages to using HMDs, such as the limited field of view. These issues are discussed in the accompanying paper. Nonetheless, we believe that these techniques will play an important part in the future of computer-supported collaborative work.